Hi everyone, Tina here, and today I'd like to talk about variable acceleration with vectors. We'll be using calculus, so differentiation and integration, to move between displacement, velocity, and acceleration. Using vectors with variable acceleration is usually something you'll come across during year 2 of your A-level course. I have made another video on variable acceleration in year 1, so I'd recommend you watch that one first if you haven't already. Go through some key ideas first, and then we'll look at some examples. So here are the key ideas for variable acceleration. Basically, to go between displacement, velocity, and acceleration, you can differentiate when you go down that list and integrate when you go up that list. This is because velocity is the rate of change of displacement with respect to time, and acceleration is the rate of change of velocity with respect to time. If you can remember that order of SVAR, that'll be really helpful in the questions. This was the idea that I talked through in my year 1 video, but in this video, I want to show you that this idea works with vectors too. Something additional here as well. Sometimes they will use the letter R to denote the position vector, and that's displacement relative to a starting point. And then sometimes for velocity, you might see R with a dot. That's called dot notation, and it just stands for dr dt. So it's another way of writing the derivative. Similarly then, sometimes for acceleration, we might see that as R with 2 dots. That's the second derivative of r, and that will be the same as velocity differentiated. Let's take a look at some examples. Example 1. The position vector of a boat sailing on a lake relative to an origin is r equals 2 sine ti plus 2 minus 2 cos tj kilometers, where time t is measured in hours. Part 1. Show that the boat is initially at the origin. So that word initially means t would be 0. So all we need to do is sub t equals 0 into the position vector. That would be 2 sine 0 I plus 2 minus 2 cos 0 j kilometers. If you work this out, you get 0i plus 0j. Therefore, the boat is at the origin. Part 2. Show that the boat takes 2 pi hours until it first returns to the origin. So if it's returning to the origin, that means that the position vector is going to be 0 again. So let's say when r equals 0, that would mean that 2 sine t would have to be 0, but also 2 minus 2 cos t would have to be 0. If you solve these trig equations separately, for this one, you'll get t is 0. And then if you think about it, on the sine graph, it would also be 0 at pi and 2 pi. For this equation, if you rearrange, you get cos t is equal to 1. Therefore, t would be 0 and also 2 pi. So the places where they match are at 0 and 2 pi. We already know that the particle is at the origin when t equals 0. So the other place will be when t equals 2 pi as required. For part B, they want the velocity of the boat at time t hours. So here is where I would write SVAR. And I would see that to go from displacement to velocity, that's going down the list, so we need to differentiate. So I'd write v equals ds dt, in this case dr dt, and that would be 2 cos t I plus 2 sine tj, kilometers per hour, and that's it. And then for part 2, they want the velocity at time t equals 2/3 pi. So all we need to do is sub in 2/3 pi into the velocity equation. So when t equals 2/3 pi, v would be this. When you work that out, you get minus I plus root 3j, kilometers per hour. Example 2. A particle moving in a plane has velocity v meters per second at time t seconds given by this vector. Part 1. Find an expression for the acceleration of the particle. So for this one, I'd jump straight into writing SVAR, and I'd see that if I want the acceleration from the velocity, again, that's going down, so we differentiate. So A is dv dt. You can differentiate vectors as normal. In this case, I would keep it in the column vector notation. So that would be 4 minus 6t, and then 12t, meters per second squared. Part 2, find the acceleration of the particle at time t equals 3. All we need to do is sub 3 into our new A equation. And that will give us minus 1436 meters per second squared. Part B, they now want the position vector of the particle given that its initial position is at the origin. Again, I would write SVAR, and this time we want to go from velocity to displacement, so that's integration. So S or R in this case, because they want the position vector, usually denoted with an R, is going to be the integral of v dt, which is the integral of the v vector with respect to time. When you integrate this, each component separately, you get 2t squared minus t cubed, and then 2t cubed minus 2t plus c. Can't forget the plus c when we're doing integration. Now we can use the information given to try and find c. So they say that initially it's at the origin. So we could say when t equals 0, r equals 0. Therefore, the c vector is also going to be 0, 0. Because if you sub in 0 for r and 0 for t, that's what you'll get for c. Therefore, altogether, we've got r equals 2t squared minus t cubed, 2t cubed minus 2t, and that's it in meters. Final part of the question, find the position vector at time t equals 4 seconds. So again, just going to sub in t equals 4. When we put that into the r vector, we get this, and that works out to be minus 32 and 120 column vector meters. Example 3. Once an aircraft reaches its cruising height at time t equals 0 hours, its acceleration is modelled by this. Given that the velocity of the aircraft at t equals 5 hours is v equals 400I plus 40j kilometers per hour, find the velocity of the aircraft in terms of t. So in this case, we're given an equation for acceleration, and we want to find the velocity of the aircraft in terms of t. So if we write SVAR, we want to go from acceleration to velocity. So that's going up the list, therefore integration. So if we do that, we say v equals the integral of a with respect to time. We sub in the a equation into the integral, and then we integrate, doing the I and j components separately. Then we have to have a plus c, and this time to find c, we're going to use this information that they gave us about the fact that at t equals 5 hours, the velocity was this. So if we sub that information in, when t equals 5, velocity is this, we get 400I plus 40j on this side, and then 5 to the power of 4 minus 2 times 5 cubed I plus 0.3 5 cubed minus 5j plus c on this side. If you tidy this up, you get this, and then you can rearrange for c, and you get 25I plus 7.5j. So c won't always be 0. It's really important that you check the conditions given in the question. Now we can write our velocity equation all together and say that v is going to be this. Notice how I've put the c components in their I and j formats with the rest of the expression. Part B, they want the speed of the aircraft when it first reaches its cruising height. Earlier in the question, it says the aircraft reaches its cruising height at time t equals 0 hours. And we also know that speed is the magnitude of the velocity vector. So if we sub t equals 0 into the velocity vector, we get this, and then we can find the magnitude using Pythagoras. That works out to be 26.100766 and more, roughly 26.1 kilometers per hour to 3 significant figures. And that's it. Example 4. A particle's velocity is modelled by the equation r dot equals this, where t is the time in seconds. The particle's initial displacement is 0, 0. Find the position vector of the particle r at time t seconds. So this is that dot notation that I mentioned earlier. It's r dot, which is the same as dr dt, therefore that is the velocity. It also mentions velocity up here, but it's good to be aware of the dot notation. We're told initial displacement is 0, 0, so that's when t would be 0, and we want the position vector at time t, so a general position vector that involves t. To do that, we're going to note down SVAR again. We want to go from velocity to displacement, so that's integration. S equals r, position vector, is the integral of v with respect to time, so we're going to integrate that v vector that they gave us. When you integrate this, you get this, plus c. Now we're going to sub in the initial displacement. So when t equals 0, the initial displacement or position vector was 0, 0. Therefore, 0, 0 equals 0.50 plus c. And that's what you get when you sub in t equals 0 into that vector up there. That means then that c is going to be negative 0.50. So overall, our position vector is going to look like this. And that's part A done. Part B, they want the magnitude of the acceleration after 1 second. So if we write SVAR, we've got velocity and we want acceleration, so we're going down the list, therefore differentiation. So if we differentiate v, we get this. And then they want it after 1 second, so let's sub in t equals 1. That would give us this. Now we can tidy this up a little bit, but I would still keep it in terms of exact values, so in terms of e and fractions. Overall giving 9 over 8 e to the power of 1.5 plus 2, and then 21 over 4. Reason being, I don't want to lose accuracy when I then find the acceleration magnitude. So the magnitude of the acceleration using Pythagoras is going to be this. And that works out to be 8.78 meters per second squared. 3 significant figures, unless stated otherwise. Last example. At time t seconds, a particle p has acceleration a meters per second squared, where a is that. Initially, p starts at the origin O and moves with velocity minus 5j meters per second. Find the distance between the origin and the position of p when t equals 6. So for part A, I'd write SVAR. We're given A and they want the distance, so displacement first. That means we're actually going to have to integrate twice. Let's start with the first integration. So to find velocity, that's the integral of acceleration. Sub in the expression for acceleration. Integrate each component, not forgetting the plus c. And then if you look back at the question, it says that initially the particle starts at the origin and moves with velocity minus 5j. So we can say that when t equals 0, v equals minus 5j. Therefore, if you sub both of those values in, you can get your c value and it's going to end up being minus 5j. Now we know that velocity altogether is 2t squared minus 3ti plus 2t squared plus 5t minus 5j meters per second. That's the first integration done. Now we need to integrate again to get displacement. So displacement is the integral of velocity. We're going to sub in our new velocity expression. When we integrate this time, we get this. Again, a plus c. Let's find this c value because we know that when t equals 0, the particle is at the origin, so displacement is also 0. Therefore, if you sub both of those in, c ends up being 0 this time. Now we know our full displacement equation is going to be this. Now we can look to finally answer the question, so find the distance between the origin and the position of p when t equals 6. All we need to do is sub in t equals 6 into that equation up there. So replace all the t's here with 6. And when you do that, you get s equals 90i plus 204j. That's the displacement. We want the distance. It's the distance from the origin, so we can just use the displacement vector as it comes. And distance is the magnitude of displacement. So using Pythagoras, that's 90 squared plus 204 squared, all square rooted, and you get 222.97, so roughly 223 meters to 3 significant figures. Part B, find the value of t at the instant when p is moving in the direction of I plus 2j. Now, moving in the direction of I plus 2j is interesting. What that means is that it's moving parallel to I plus 2j. That means we can say that v is going to be a multiple of I plus 2j. Because with vectors, when two vectors are parallel, they are multiples of each other. And we're going to say that k has to be greater than 0, so it's definitely moving in the exact same direction, rather than in the opposite direction. If we expand this, that's going to be ki plus 2kj meters per second. You can use any letter there, you don't have to use k, but usually we use k. Now we also know from part A that velocity is equal to this. So now we can set these components equal to each other. So we can set 2t squared minus 3t equal to k. We can set 2t squared plus 5t minus 5 equal to 2k. These are simultaneous equations that we want to solve. You can do this however you like, but I'd probably take this k and sub it in here. So that would give me 2t squared plus 5t minus 5 equals to 2 times and then 2t squared minus 3t instead of k. Can then expand and simplify. Move everything over to one side, so you get a nice quadratic equal to 0, which you can then solve however you like, and you get t equals a half or t equals 5. Now we've got two potential t values there, but both may not be valid, so we need to check. When t equals a half, a would be equal to -1, so this means it's invalid. As we said, k has got to be greater than 0. So this solution is invalid. This one, when t equals 5, k is 35, and that's fine. So the final answer is t equals 5 seconds. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else you think might find it helpful. Thanks, and see you next time.